Okay, let's get started here, please. So all of you should have received your assignment number 2 back. Again, the grades were good. The main comments that I had about it was similar to the last assignment. Be careful with the efficiency of the code that you're writing. So, for example, I had a number of groups do this. Oops, sorry, I didn't have this up immediately. There we go. So, for example, in number 1C, basically you needed to find, what was the probability that t was greater than or equal to 18 given f hat. And so what you had was maybe, let's say, a vector of your t stars, which I just called t dot star. And the most efficient way to find what this probability is just to look at how often is t star greater than or equal to 18. And so you can take advantage of the way that R does its calculations with vectors. Rather than what some of you did was you wrote a for loop and you checked at each individual element of t star one by one, and then gave it a 1 or a 0 depending upon what was greater than or equal to 18. That's quite inefficient. While it's correct, and I wouldn't take off points for it, what you should strive to do is better. You should try to be a better with R, and so that's a very common thing that, let's say, beginners of R make that kind of an error, and let's hope that you can become more advanced through taking this course. Also, then on 2F, part I, so I gave you this expression for the asymptotic distribution of a correlation coefficient. And what you need to do was then show me how then this confidence interval expression comes about. And a number of groups were making an error right here in the very first step. They were putting an equal there as the first step. But again, and that is incorrect. And again, the reason is because we're looking at this gives us as n goes to infinity. And so that's why this needs to be an approximate rather than an equal. It's a minor thing, but like if you were to do this in a paper, let's say that you're writing for a stat journal, your paper could likely be rejected just for that simple part right there. Okay. Okay, that's all I had specifically to discuss. Do you guys have any questions regarding the assignments? Okay, let's take a look at the schedule then, where we're at this semester. So we'll continue with the bootstrap today. We will do it also tomorrow. There's a small chance that we will get to parallel processing. Probably will not, but a small chance. The midterm will be Tuesday, March 10th. I have written a good draft of it over the weekend. I still have to do some minor modifications to it, but I have a general idea of what it's going. I have a very good idea of what it's going to be like. Specifically, if you've had me for a class before, it's the same format as my other tests. If you haven't had me for a class before, what that means is that it will be a computer-based test. You will use the computers here in the classroom. I will give you a printed copy of the test, and you simply use the computer essentially as your calculator to do the various calculations that you need during the test, and you write your answer on the paper copy of the test. It is closed book, closed note, but you can access any of my R programs that will be available that are available on my website. So it will be very advantageous to you that you make sure that you're familiar with my R programs. I would assume that you already are in order to do the previous assignments, but just in case you aren't, you should be. Okay. And then we will spend part of the class period then on March 5th reviewing for the exam. It will just be over the Monte Carlo simulation and bootstrap sections. Are there any questions about that brief introduction to what the exam's about? Okay. Assignment number 3, we will spend part of the day discussing that. Ideally, it would be nice if we can have that finished before the midterm, and hopefully, ideally, I'd be able to get it back to you before the midterm. We'll just see. So for right now, we're going to make a tentative due date of March 6th at noon, and hopefully then that Friday afternoon I can grade it and get it back to you. And 2 more things. Also, next time we're going to start talking about these presentations that will be done at the end of the semester. I would imagine that probably right after we get done with the midterm, you really want to start spending some time thinking about what you're going to do for the presentation. I have written up a description, a 2-page description of what I'm expecting for these presentations. It's available on the Graded Materials webpage if you want to take a look at it now. At least before our next class, download it so you can bring it to class and take notes on it. So we'll talk more about presentations next time. And then lastly then, I was looking in terms of what I expect to occur for the rest of the semester in terms of grades, in terms of the number of points that we're going to have. And so far, including assignment number 3, we have 115 points. The midterm will be 100 points. I anticipate, notice I say the word anticipate here, for the rest of the semester, after that midterm, we will have 100 points for the presentation. And then approximately, okay, I got something wrong here. Shoot. Okay. Does anyone remember how many points assignment number 1 was worth?
5.
How many? About 47? Okay. And the last assignment was worth 58. And the next one's worth 44. So that's, let's see now, 105, 159, 149. So far we've had 149 points. So assignment 1, 2, and 3, midterm 100, presentations, or the presentation that you give will be worth 100 points. And then I anticipate about 115 more points for assignments after assignment number 3. So in total, that's going to leave us, maybe about 434 for the semester. Now it could go up to, could get closer to 500. It could get closer to 400. But I thought it would be good at this point to tell you what I anticipate what will be happening, since we're just simply taking the number of points that you've earned over the number of points possible for your grade. Also, this will allow you to see, well, just how big is this midterm relative to your overall grade that's coming up. So it might be about somewhere between 20 and 25%. Any questions? Okay. Let's see. So we left off on about page 81 of the notes. We were talking about the bootstrap with respect to hypothesis testing and Larry Bird. So here is the Larry Bird data once again. And what we like to do is test for independence between the outcome on his first attempt and the outcome on his second attempt. And so to do this, we're going to use the Pearson chi-square statistic. And we're going to calculate that for every resample. we talked about two different ways to take a resample. The first way we're going to actually implement in class. The second way, you can think of it as a homework problem. It's not going to be difficult to do. And if you do want to see how I've done it in the past, you can take a look at my fiber.r program on my books website. So the first way then is what we're going to do is we're going to independently resample with replacement the first variable values from the second variable values. What I mean by that is that we are going to transform our data into what I often refer to as a raw format, where basically we have a data frame where we have one variable that contains all the responses for that first attempt. And then we also have another variable in this data frame that corresponds to the second attempt. And so what we're going to do is simply resample from the first variable, resample with replacement. And also, we're going to resample with replacement from the second variable. And we're going to do this process independently. The reason why we do this process independently is because we need to resample under the null hypothesis, which says first is independent of second. Okay? Once we get these two, let's say, resampled vectors of data, we're going to basically put them back together into a data frame and then calculate x squared, our Pearson statistic, which would be x squared star then in that particular case. Okay. Is everyone comfortable with that so far? Any questions? Okay, so now bottom page 81. Now, in this situation, and there's a few others where this happened, you have to be very careful. And the reason why we chose x squared was because it was an asymptotically pivotal statistic, meaning that it will have a distribution that's not dependent upon any parameters for a fixed table size. So, when you're doing this resampling process, is it possible that maybe the number of rows could be reduced in a resampled data set in comparison to your original data? Alternatively, could the number of columns be reduced for a resampled data set in comparison to what you originally observed? And the answer is yes. Because remember, we're resampling with replacement. And it is possible that when you do that resampling process, that maybe you don't necessarily observe every column that you originally had. So equivalently, you can think of it as in a resampled data set, maybe you have no misses for that second attempt for Larry Bird. That could happen. It's not going to happen here, but it could happen. I will show you an example where it does happen later. Well, what does that mean then? Well, if you were to calculate your x squared statistic then on this resampled data set, well, what's that asymptotic distribution for that statistic? Well, it's not the same as it was for the original data. So now essentially your distribution is changing due to the resampling. We can't have that happen. So because of that, you need to do a conditional resampling approach, meaning that if the dimension of the table changes in comparison to what it was originally, throw that resample out. Do not include it in any of your calculations. Well, then you might be thinking, well, yeah, okay, that makes sense for, if it happens just a few times. But what happens if, you got R equal 4,999 and it happens 2,000 times? Well, that could cause problems. And so you might want to think about doing alternative testing methods than using the bootstrap. And I will show you one called permutation tests later on where that does not happen. Okay, so we need to watch out for these kinds of things that occur. Okay. Well, in order, now, especially for hypothesis testing, using the boot function to take the resamples can somewhat be, I don't want to call it difficult, but how should I put it? Odd? That's not the best word. Can be sometimes more trouble than what it's worth. And the reason is because, remember, we need to resample under the null hypothesis. So we're not just easily resampling the data like what we did with the AC data, or with that CD4 counts data that we did before. We have to resample the data essentially in a different way. And that's what makes working with the boot function not necessarily always the easiest. With respect to now testing for independence in a contingency table, you can use the boot function. I'm going to show you how. I'll let you make a judgment if it's really worthwhile. I don't think it's really too difficult. But I think, as you'll see here shortly, it's like, you have to do that? Why don't you just use the sample function? Okay. So now, in order to use the boot function here, I'm going to have to change the format of my data set. So I can do what's called a stratified set of resampling. And what I'm going to do in my data set, get my data out. Okay. Oops. So again, this is what my data set looks like. And I need to rearrange the data set so that basically that variable called first is going to be in the first column of my data frame, and then I'm going to put the variable second right below it in my data frame. And then I'm going to create a new variable that basically tells me, well, was this response that we have here for first, or was it for second? In other words, was it for the row variable, or was it for the column variable? This is how I can do it. So I use the data frame function. I create a variable called index, and I take that first column out of my original data frame. And then a way to label that this indeed was from my rows of my data set, rows of my contingency table, I have a variable called table.part, and I let that be equal to x. Because remember, we let x correspond to my rows of my contingency table. So then also I'm going to form another data frame where I have exactly the same variable names in it, but now I'm going to put all the responses from the second free throw attempt right below those from the first free throw attempt. And then I'm going to label it by table.part equal y. And so if I put that in, and then if I bind it together, put it into set 3, this is what I get. So that now I can tell the boot function to perform a stratified resample where I say, okay, resample within table.part. So wherever you see an x, resample those index values. Wherever you see table.part equal y, resample those values. This is how that can be done.
I have a question.
Yeah.
The data doesn't need to have the column component bar with the transit.
I'm sorry, could you restate that, please?
The data set doesn't need to have that column name table bar.
It does. You'll see why. Okay. So I set a seed, I set the number of resamples that I want. I use the boot function. I pass in this new data set. My statistic of interest is going to be calc.t. You'll see how to do that shortly, or see how to do the calculation shortly. Number of resamples. I am doing non-parametric resampling. And then here is my argument called strata. This tells R to resample within table.part. So that's the only way that you can actually specify, yes, do your resampling within everywhere you see those X's. That's where I want you to do a resample. Everywhere you see the Y's, that's where I want you to do a resample. Also now in my calc.t function, I have another variable or another argument called dim.table, which stands for dimension of the table. And I just put in here the number of rows and number of columns that we had originally with our contingency table. The reason being is because remember we need to make sure our resamples have exactly the same number of rows and the same number of columns as what we had originally. So let's go back up to calc.t. Just as we've done many times before, I have an argument called data. I have an argument called I for my indices. And then also I have this additional argument dim.table. Remember how the boot function has the ... argument? That's why I was able to put in that dim.table part for boot. And I can now pass that in to calc.table. I'm sorry, calc.t.
You must have that argument in the boot function.
Yeah.
Table.
If to pass it in to calc.t, yes.
Okay.
That will be the better way to do it than simply to hard code it inside calc.t in terms of 2 by 2. Okay.
Some of the notes missed that part.
Oh, I'm sorry. Yes, yes, and in fact, if I was going off of my printed notes, there you see it in blue. I guess it doesn't help to put it in blue there if I don't actually use these notes. There will be more than usual a number of changes in the notes today, so please be careful. Okay. And also, I have this in blue here. Was that a problem?
No, that's there.
Okay.
It was
It was uppercase
okay.
by mistake.
Upward.
Okay. Okay, so the first thing that I do is I find my resample. Once the original data is passed into it, just like how I've done before. Since this is a data frame, notice how I have an I here. I'm sorry, I have a comma after the I. And what you would see if you actually were to print out the indices, you would see for the first 338 values of I, they're always numbered between 1 and 338. We do have 338 observations, right? Yes. Then the next 338 observations will always be numbered between 339 and 676, yes. Because I'm doing the stratified resampling. So it's just a good constructive thing that you could do is to put a print statement in there, use the boot function for one resample, and you'll see it. Okay. Next, what I need to do is then basically reconstruct my data so that I can work with the chi-sq.test function, which we used last time to perform a regular old Pearson chi-square test for independence. So what I do then is I just simply pull out all the observations that correspond to x. So I get a bunch of trues and falses there. I pull that out, put that into x. I do the same thing for y. Then I use chi-sq.test, where I have just the index values for x, just the index values for y, correct equal false, and then x.sq contains all the really good things I need. Next, I do my table check. So I check. I'm going to find the number of rows that are in the observed element of x.sq. That observed element, as you might expect, contains my contingency table. Now for my resample. So I check. Is that equal to the number of rows that I had originally? Yes or no? If it's yes, check or ck.row gets a 1. I do a similar thing for the columns. And then I pass back x squared, my check for the rows, and the check for the columns. So that when I try this with my original data itself, I get exactly the same as what was observed. Any questions?
So x $sign index is giving us the
Yeah, because remember how we structure the data.
Okay, so it's giving us the mates.
And I had put that into x.
So the ck dot row and ck dot core is just to check the dimension.
Yes.
Not
It's checking to make sure that the number of rows or the number of columns are exactly what was observed.
but not not check the number of the observed. Just check the dimension. Just a 2 by 2.
It's checking to make sure it's essentially it's 2 by 2.
Only 2 by 2.
That's what the bird data was, 2 by
Okay.
2.
But the calc.t won't arrange the data back again, right? Do we have to we just need the chi-square value, so we don't have to rearrange the resamples again?
Well, we need to put the resample in a format that chi-sq.test
Right.
will actually calculate our x squared
Right.
statistic. And so that was the purpose of, this is what I would call rearranging right here.
Okay.
And then I put it in the corresponding spots. So essentially, and you know, maybe it's because since we did this on Thursday, I'm using essentially the same code that we did on Thursday
Right.
to do this part right here. And again, you know, if something's not clear, you know, put some print statements inside this function. Run it. See what happens. And you'll say, oh yeah, okay, that makes sense. Hopefully. So when I run my boot function, then I get some results. You know, in general for bootstrap hypothesis testing, you know, some of these results that you see here may be meaningful or not meaningful, because remember, you know, not as much so here, but in other cases where we had to basically adjust our data. If you remember when we did a hypothesis test for mu or mu1 minus mu2, when we had to adjust our data, remember we don't have the original data itself that we're actually resampling. So in that case, some of the stuff that you get for this bootstrap statistics may or may not be meaningful to you. So just realize that. The second and the third elements, remember that corresponds to our check row and check column. Now notice what it was for the original data. Also notice the bias and the standard error is 0. So what does that mean, do you think? Everything's equal to 1. And so everything's correct. So if I had some non-zero values pop up there, then I would start to worry. And I would investigate this more. Now there are some warning messages that pop up here. And so I type warnings. And we see some information about chi-squared approximation might be incorrect. Nothing to worry about there. This automatically will be printed by the chi-sq.test function if any estimated expected cell count is less than 5. If you look at the code for that function, you'll see that. And that's how I discovered, yeah, that's not really, doesn't worry me at all. You know, I just need to use this function to calculate my x squared. Now there are ways that you can actually turn off the warning messages, but I don't recommend doing that just in case you get some other kind of warning messages for some reason. So now I can calculate my p-value simply. So all of my x squared stars are in the first element or first column of my t component of boot.res. And so what I'm going to do is look at what proportion of them are greater than what I observed my x squared to be. And so I can pull that out by using the t0 component. Please make note of this, that again, depending on the type of hypothesis test that you're doing, this value here may or may not, in general, be what you want to use. Again, when we were looking at hypothesis test for mu, we had to adjust our data. So the t0 component will not be what we actually observed, because with the boot function here, we are resampling. With the boot function, we would be resampling adjusted data. So please, please take special note of that. Is that clear? Because I want to make sure that there are no mistakes in the future. Because it's easy to make this mistake. I've made it before.
Say that again.
Sure. Okay. So sometimes when you do bootstrap hypothesis testing, you have to adjust your data. And you use the adjusted data then right here in the data component of boot. So your T0 that you get out from the boot function may not be, let's say, the observed value of the test statistic itself, Rather, it will be the observed value for the adjusted data, which is not what we want to compare to when we are doing the p-value calculation. Does that help?
So in this case, they're both the same.
They are
So
both the
that's
same.
why it's not a problem.
Yes. And if I had to do this over again, I probably would have purposely just saved my original x squared someplace else and used it there. When I was reading over the book, my notes last night, I was like, oh, maybe. Well, it works fine now. It might cause problems later on.
So is it advisable to do the x squared first, like when you have the data set and just do the x squared
Sure.
with that and then compare it to that?
Yes.
Okay.
And I think, generally speaking, you would calculate your statistic itself before you did any kind of bootstrapping, no matter what.
Mhm.
So, you'll have it available. You
Right.
just need to put it in the right spot. Excuse me.
It's something like using the mean of y, like when we assign t, rather than using the t naught.
Yep. Okay, so essentially what I'm doing is calculating the proportion of these x squared stars that are greater or equal to what was observed. In other words, I'm measuring how extreme is the observed value of x squared now relative to this distribution that I have just simulated under the null hypothesis. And what I get is a p-value of 0.6052. The actual p-value that we got from using a chi-square 1 approximation was 0.6015. So, just about the same. And again, these are, would I use the bootstrap for the Larry Bird data in actual practice? Well, no. The reason why I do this here is because all of you would probably have seen a Pearson chi-square test before in some format. And so we have a way to make a comparison. And so I'm using this as a learning tool, not necessarily as what one would do in practice. Okay. So if we go to page 85, and just to show you what one of these contingency tables will look like for a particular resample, I decided to pull out the third resample. You can take a look at the details of how I did this on your own, but this is what the actual contingency table looks like for the third resample. So third right there. I use the boot.array functions we've done before to pull out resamples. And again, we can make a comparison to what was actually observed. And we can see, obviously, there are differences. One thing that I want to point out that will be especially important later on is take a look at the marginal counts. So for the resample, we had 282 and 56 for the row marginal counts. For the original data, we had 285 and 53. Okay? Notice that these marginal counts can change. You can do the same thing with the columns. Shortly, we're going to look at a procedure where these counts will not change. And you'll see why that's important at that time. Please note the small little error here on the bottom of page 85. So now to begin with here, if you remember, we saw that there was one small cell count in the Larry Bird data. In fact, and whenever you see a small cell count in a contingency table, you might start to worry about, well, is this chi-square approximation actually going to work or not? And more formally, you can compare it to the estimated expected counts, and in that case, it's not going to be as big of a problem, or will not worry you as much. But whenever I see small cell counts, I always get worried. And so, as we've discussed before, one of the things that the bootstrap allows you to do is to make a judgment of if certain distributional approximations that you're using, if they're accurate or not. Is this chi-square 1 really accurate? You might be thinking, well, yeah, it is. We got about the same p-value. Well, that's not enough. Okay, that's only at one small area of that distribution that you're actually making that comparison. So just looking at the p-values, comparing the two p-values is not enough. Instead, you have to actually look at the whole distribution. And so what I did was, I wrote a function which I called summary, or summarize for the lack of a better name, where we'll get some graphical displays of what we get from the bootstrap and compare it to a chi-square 1. I'm just going to briefly talk about this function. I want you to look at the details on your own. The first thing that you pass into the function is result.set, which is basically all my x squared stars. Then I pass in my observed value, my statistic, called statistic. That's going to be my x squared. I pass in the degrees of freedom and the number of resamples. Inside my code here, inside my function, you see I'm going to create a histogram with a chi-square 1 overlay. I'm going to plot my EDF of my x squared stars with a chi-square 1 overlay. And then lastly, I'm going to do a QQ plot. And I guess at the very end, the p-value is automatically returned. So you will often always want to do stuff like this whenever you use the bootstrap. So you can modify this function for your own needs for other distributions as well. So I run the function. This is what I get on page 86. Please note that there's a small error where you see perm circled in blue. That should be you could just put EDF. That'll be fine. The code in summarize function should also be fixed. Okay, on the two plots on the left, the red line corresponds to an actual chi-square 1. And so we can see that indeed that the histogram and EDF follow very closely to the chi-square. So that makes sense to us then why we got p-values that were so close. Any questions? Okay. Well, let's look at a place where the bootstrap fails. This is another testing for independence problem in a contingency table. Comes from Agresti's 1996, his first introductory categorical data analysis book, Table 210. For some reason, he decided to take it out of future editions. And here's what the table looks like. There are 3 rows and 9 columns. This is on page 89. So immediately, what stands out? Got lots of zeros. In fact, look at the counts for some columns. 1. Okay. Now, take this then with respect to what we saw with the bird data in our discussion about contingency table size. Hopefully, you're saying, yeah, I could definitely see situations where I do not observe 9 columns in a resample. And in fact, that's what happens here. So what I did was I basically just took all my code that we had applied before with the bird data and put it here now for this new data set. So I'm not going to go over the details, but rather the results. X squared itself is 22.2857. If I were to use a chi-square 1 distribution as an approximation, I get 0.1342. Notice the warning message that R gives us here, that the chi-square approximation might be incorrect, because we have very small estimated expected cell counts. Then with the bootstrap, we follow the same procedure as before. Take a look at the results from my boot.res now. The second and third row, my bootstrap statistics, notice the second row, seems like everything's okay, but that third row, uh-oh, I got some non-zero values there. So what that's indicating to me is at least sometimes I'm not getting a 3 by 9 table. And in fact, if I were to use the column sums or col sums function R, which basically calculates the sum of columns in a data frame, and just work with the second and the third column, which contains my check row and check column, notice that for all my rows for 4,999 resamples, everything was okay. I observed all 3 rows every single time. But for columns, only 100 of the 4,999 times did I actually observe a full-size table. Big problem. So if I were to use a conditional resampling approach, then that would say throw away 4,899 resamples. Well, that's not good to do. That's just too much. You're not going to get a good idea of that of the distribution of this statistic. So because of that, I would not even use the bootstrap here. Any questions? Okay. We got 2 more things I want to talk about for bootstrap hypothesis testing. That won't take too. Yes.
Sorry, can you, with the part in blue,
Yep.
is that a plus between the 2 terms?
Yeah. This is, I mean, it's not a big deal. I did put that in there. It's just more of a fancy way to say, to check how often do you get a full-size contingency.
Okay.
You know, especially in cases where both the rows and the columns might have problems. This is just a fancy way.
So is the equal to
Well, remember, the check row or check
Oh,
column is equal to 1
2 to 1.
if it works, if you get the same size. So I do the logical comparison there. Okay. Now you can see that having to resample under the null hypothesis really makes bootstrap hypothesis testing, I would say, takes it to a new level in terms of difficulty in comparison to what we had done previously. And, you know, unfortunately, it's very problem dependent about how do you take your resamples under a null hypothesis, which is not necessarily ideal to have. But there is an alternative approach which is not problem dependent exactly, meaning that you can essentially apply this idea to any problem. And this is how it works, real briefly. It goes back to this multinomial distribution that we saw as a way to think about how resamples are taken. And if you, hopefully you remember that basically what we're doing is that we have a sample size of n, we have n categories, and each category has a probability of 1 over n associated with it. Okay. Now, if you were to look at this from the perspective of, let's say that the null hypothesis is true, and try to essentially adjust your data, or I'm sorry, essentially try to take a resample such that the null hypothesis is true. You can do that by changing all these 1 over n's to something else. So maybe the first observation might have a probability of 2 over n being selected, and maybe the last observation has a probability of 1 over 2 times n to be selected. So in other words, again, try to adjust your probabilities in your categories in such that the null hypothesis, when you're taking the resample, will be true. What this ends up being is a difficult optimization problem. So in other words, what we try to do is, if you've ever heard the Kullback-Leibler information number, anybody heard of that before? Okay, good. You typically like an advanced inference class, you learn about that. And what we try to do is we try to minimize the discrepancy between, you know, what we would normally have and then what we should have under the null hypothesis. Try to minimize that in order to find these guys. And this becomes a rather difficult optimization problem. And because of that, I really don't see a whole lot of people using it. Even though it is really nice, it's really general, I really like it. I think it's kind of cool, to be honest. But I really don't see a whole lot of people using it. If you want to know more information about it, You can take a look at these references there. I will not ask you a question about it on an exam. I have tried it once when I was working on my dissertation. I couldn't get the optimization to work, unfortunately. Okay, so far, we really haven't talked about too much about, how do you choose the statistic that you're looking at? Like when we were looking at comparison of means, I said, well, why don't we just take a look at y bar 1 minus y bar 2, take that as your t, let's say, and calculate that essentially for every resample. Now, what you could do, because remember how the bootstrap typically works better when you have a pivotal quantity that you calculate for every resample. And so similar in the idea of that studentized confidence interval that we saw, you can calculate essentially a studentized statistic for every single resample and use that to help you do your test. And so in general, let's say that I want to test is theta equal to some constant theta 0 versus is theta not equal to theta 0. Then my test statistic for my observed data could be something like this. It was called Z0. It's equal to your test statistic, or your, let's say your statistic of interest, that's a better way to put it, T, subtract off what I hypothesize my parameter to be, divide by the square root of the estimated variance of my statistic of interest under the null hypothesis. So again, you always need to incorporate the null hypothesis. Even when you're not doing the bootstrap, you should always calculate then that variance under the null hypothesis. Very, very often in statistics, though, we don't. Because we know if the null hypothesis was true, essentially V is going to converge in probability to V0. But if you have an opportunity to adjust your variance so that it is under null hypothesis, you should. Then for every resample, do kind of like what you would expect. Z0 star is equal to T star minus theta 0, divided by then the square root of V star. And, let's say that you had a two-tailed test p-value. What would be the two-tailed test p-value? How would you calculate it then after capital R resamples? That's not a rhetorical question. This is a question that I'm asking to get a response. Two-tailed test, so you're going to start off with a 2 times minimum of there's a lot of, I'll just write it out. I'll do this. Okay, that's one component, the minimum of that, and I'm running out of room, so I'm going to come up here. And there we go. Again, all you're doing is trying to look at how extreme your observed value of Z0 would be relative to this distribution. And since we don't necessarily have some kind of named distribution that's continuous, we simply look at proportions. How close am I to the left? How close am I to the right? Is there a question?
And we have find T0 for each sample.
Find Z0 for every resample? Is that what you
Yes, and D0.
Yeah, for every resample, you would need to find a T star, you would need to find a V0. Just like what you did with the studentized confidence interval. Of course, you could do one-tailed tests as well. You should think about what that p-value should be. It's just, you know, essentially the same as what I had introduced before when we were just working with only t itself. Okay. Now there's a different way that some people think about bootstrap hypothesis testing, where they will always calculate one of these studentized quantities. So here's my hypotheses again. I calculate the same observed value for z as before. But here's the big difference. For each resample, calculate this. Z star is equal to t star minus t over the square root of v star. Notice the difference. Before, instead of t there, I had theta 0. So notice you don't see a little subscript 0 there anymore. And in fact, you don't have to resample under the null hypothesis. You just take resamples like you would normally. Now you might be thinking, wow, that solves your problem that you were just talking about, Chris. That, you know, having to resample under the null hypothesis is a pain. Well, yeah, it would if this worked. What ends up happening very often is that you have very poor power if you use this approach. Your size of your test will be correct, but you have very poor power. And there was actually, essentially, you could say the equivalent of an argument in the literature, well, about 20 years ago, about this topic. Peter Hall, you remember him from the Studentized interval, and Wilson advocate this method that I just talked about, of not having to resample under the null hypothesis. And so they had a paper that was published in Biometrics. And unfortunately, also, the authors of one of the recommended books for this class, this Givens and Houghton, also say to do this approach. But they have very little about bootstrap hypothesis testing in their book. And obviously, that was a quick way for them to solve then how to do bootstrap hypothesis testing. They could just say, oh, do this approach. Then Rob Tibshirani in 1992 wrote a reply to the Hall and Wilson paper, or like a reader reaction paper, and basically said, no, you don't want to do that. So Tibshirani was Efron's student, by the way, and also the co-author of Efron and Tibshirani, one of the big bootstrap books out there. Tibshirani's well known in statistics. And he said, no, you should not do that because of what I was just saying about the power and stuff. Now, in some specialized situations, including the one that Hall and Wilson give in their paper, you will get equivalent results. But in other situations in general, you're not going to. My one experience then with this Hall and Wilson approach basically confirmed what Tibshirani said. For my dissertation, I tried to, my dissertation actually really heavily focused on bootstrap hypothesis testing. And I tried to do my hypothesis test for a particular problem like how Hall and Wilson did. And my power was just horrible for my test in comparison to when I did take resamples under the null hypothesis. So I bring this up because you still might see some people, including the authors of one of the recommended books for this course, say to do this, but I strongly recommend against it. Okay, so that takes us into something called permutation tests. But before we do that, I want to talk about assignment number 3. So if you have a copy of that available, let's talk about that. So it was either last summer or last fall, I came across a blog post that talked about this video that I cite here. And I watched the video and I thought, oh, you know, that would be a great, nice little problem to work with for my computational statistics course. And so I decided to construct an assignment with respect to it. And the main question of interest in this this video here, and then the corresponding paper for it was, does drinking beer make you more or less attractive to mosquitoes? What that basically means is that, you know, let's say if you drink some beer, will mosquitoes be more likely, let's say, to bite you than if you had not drank beer? So obviously, you know, if you drink beer, you know, you might emit beer fumes. I guess that's the only way to put it, as you perspire. Anyway, so I'm not for sure who this person is exactly. John Rouser was at a conference, and they videotaped it. And it was a conference of primarily non-statisticians, but people who analyze data. So data scientists. So he was talking to them about some of these resampling methods and how, you know, they're so more intuitive than necessarily using the old-fashioned t-test to do like a hypothesis test to compare two means. So take a look at the video. The video is only about 11 minutes. And he cites this as this paper here as a source of the data, although unless I missed it, I cannot find the actual data in there. Instead, what I did was on the video, he actually, it's a small data set, he actually put the video up on the slide. So the data is in mosquitoes.csv. You can download it from my webpage. And this is what it looks like. And so in this experiment, people were essentially randomized to a beer treatment group and also a water treatment group. So some people were given beer to drink. Then they go sit down in this controlled setting, and the experimenters release some mosquitoes, and they examine how many, or they counted the number of mosquitoes that were attracted to that person. Without going on the details, if you want the details, take a look at this particular paper here. So, for example, for the first person who was in the beer treatment group, they had 27 mosquitoes that were attracted to it. For the first person, for the last person in the water group, they had 20. And so what we're interested in knowing is that if you drink beer, will you be more likely to have mosquitoes come to you than if you had drank water? And you know, the whole purpose of this, and you, again, read the paper, is, you know, this might be of interest, especially in countries where there's problems with malaria, for example. You know, and the malaria prevention methods that, you know, obviously that mosquitoes carry that. Excuse me. Okay, so the beer group is going to be group 1. The mosquitoes group, the water group is going to be group 2. And so to begin here, what I want you to do is simply perform a standard t-test of mu1 minus mu2 is equal to 0 versus 9.7. Okay. You know, if you remember from your first stat course, you can do it with either equal variances or unequal variances. I want you to do both. The results will be very, very similar. Does anyone know of a quick function that would do this test in R? Excuse me?
T.test.
Yeah, t.test. So I recommend using that. Now, in part B, of the at about 6 minutes and 50 seconds into the video, Rouser says that so he does the regular old t-test, first of all. And then he says, only a few people in this audience have any idea how this argument really works, that you have this t-test statistic, you have this t-distribution approximation. Only a few people in that audience of data scientists really knows why that works. Well, since you are all statisticians, you should know why it works. I want you to explain it to me why it works. Part C. So we're going to use the bootstrap. You set a C number of 8199 before you take any resamples, and use 4,999 resamples. What I want you to do is implement approach number 1 on page 72 of the notes for testing the difference of two means. So if you remember, there was 3 approaches that I gave you. I want you to implement approach number 1, where you're going to use the difference of the 2 sample means as a statistic of interest. Obviously, this is going to be a 2-tailed test. State the p-value. Also, construct a histogram of the t-stars. And show me where the observed value of t falls on that histogram to relate it to what the p-value is telling you. Then, implement approach number 1 again, but now use the studentized statistic. We just talked about studentized statistics, so call that Z0. State the final p. The advantage of using that studentized statistic is now we can make a judgment about using a regular old t-distribution approximation, because this is essentially one of those t-test statistics that you would use in part A. So, determine if there's enough justification to use the t-distribution part A from using now your resamples that you just got. So what would you maybe do? Excuse me?
Histogram and put the histogram of those.
So draw a plot, histogram, yeah, sorry. Yeah. So you could do a histogram, that would be one approach, similar to what we just did with the chi-square distribution. In fact, what I did for my answer key was I adapted my summarized function for this problem. Part 4 here, implement now approach number 2. That's on page 72. Use then simply this difference of the sample means for the statistic. Okay. Part D now asks you to do a permutation test, and then we're going to talk about permutation tests next in the set of notes, so I'm going to skip this. And then, you know, originally last fall or last summer when I first saw this blog post and watched the video, I thought, you know, this is you know, a nice, realistic problem that I can use again with the computational statistics course. And then, you know, so I started, you know, last week I started writing up the project or the assignment here, and I thought, you know, I better take a closer look at that paper. And I did take a closer look at the paper, and I found out that, you know, it was somewhat questionable if I would have took this approach with this data, if I would have known everything about it that I do know now, given that I read the paper. Specifically, and hopefully, you know, you were thinking about this when I first introduced this to you. You know, 27 mosquitoes were attracted to a particular person. How many mosquitoes were originally released? Or how many mosquitoes is this out of, essentially, that could have been attracted to that person? Because you can imagine a scenario where someone's put into a room where there's no mosquitoes. Well, of course, that value is going to be 0 in terms of the number of mosquitoes that are attracted to them. So, you know, you need to take into account just how many mosquitoes were given the opportunity to be attracted to a particular person. And so now this turns this into more of a binomial problem. So in each of these cases, from reading the paper, what I think happens, what we will assume actually did occur, 100 mosquitoes were released. So that first person, 27% of mosquitoes were attracted to them. Is everyone clear on that? So given that we have binomial data then, we can approach this problem from a different point of view. Definitely, if you've had my SET 875 course, you should know this. But you should also if you've had SET 971, which is a prerequisite for this course, and that is you can use a generalized linear model. I guess that would be one approach. I guess you could do a, yeah, I guess I didn't even think of, well, yeah, I don't know why I didn't think of this when I was writing up the project. You could use simply a hypothesis test for the difference of 2 proportions. I chose the more general approach, and that is to use a generalized linear model, specifically a logistic regression model. So, given this scenario, what logistic regression model would you want to use here? So logit of pi, where pi is the probability of being attracted. What should come next? So I want to write out a logistic regression model. No, don't think in terms of pies. Don't think in terms of pies. Yeah, think of it in terms of like a regression model. So beta 0 plus times the treatment. Yep. So I want you to estimate that model now. If you've never done this with R, it's not too difficult. Use the GLM function to do it. If you need help with it, I'd be more than happy to show you the exact way to do it. I would imagine that all of you have seen how to do it in SAS. It's just as easy in R. I recommend using the GLM function to do it. And I want you to perform a regular old likelihood ratio test to test the hypothesis. Use a regular old chi-square distribution approximation. What will be a function R that will allow you to do the likelihood ratio test easy? For those of you who've had me at least for 875. ANOVA. So for example, I would use typically the capital ANOVA function that's in the CAR package. You probably could also do it with what's called the little ANOVA function that's in the stats package too. Then next what you're going to do is use the bootstrap to do this test. Now, since we're using a regression model here, we haven't really talked about how to do bootstrap hypothesis testing with respect to regression models. The next set of notes after we get done with permutation stuff talks about regression models. So you're not going to be able to do, I mean, you could probably guess how to do it, but we haven't talked about more of the details of how to do something like this yet, but we will. Okay, so that's assignment number 3. Are there any questions? Okay, so let's get back to the notes then with the remaining about 5 minutes. So we're going to talk about permutation tests. They're sometimes called randomization tests as well. I prefer the term permutation test because what we're going to do is permute our data. What the word permute basically means is you could say mix up stuff, rearrange stuff. And that's what we're going to do with our data. We're going to just rearrange our data values to do this test. In fact, some people think of permutation tests as actually a special case of the bootstrap. The key difference is with the bootstrap where you take resamples with replacement, permutation tests take them without replacement. So we take resamples without replacement. You might be thinking, well, wait a second. So that means you're going to get the same data set every single time. How's my statistic going to change for every resample? It all comes down to how you take in your resamples with respect to the null hypothesis. Okay? You'll see why your statistic does change from one resample to another. If you would like a bigger introduction to permutation tests, an excellent book out there, even though it's about 10, 11 years old now, is Jim Higgins' Introduction to Modern Non-Parametric Statistics. Jim Higgins is now he's a retired professor from Kansas State. And back in fall 1995, when I took his non-parametrics class, we were his first guinea pigs for the book that he was writing. So it was in 95, so it took him, as you can see, 9 years to get it finally published. Now I don't feel as bad about taking 3 years with my book. Anyway, it's a good book. One of the key elements of doing a permutation test is that we have to talk about a sufficient statistic. Obviously, all of you have had that. It's at 883. And these hypothesis tests are conditional tests. They're conditioned on the sufficient statistic. What that means for us is that for every resample, our sufficient statistic, the actual observed value, has to be exactly the same. And the way that we get it to be exactly the same is that we resample without replacement. So that's the key. And I'll show you some examples where, yes, every resample, we are having the exact same sufficient statistic. Now, the most general way to think of, well, what sufficient statistic that you're going to have is essentially the order statistics for a data set. So the order statistics have to remain the same. For specific cases, like with the we're going to look at hypothesis tests for independence again in terms of contingency table structure. In those particular cases, those sufficient statistics become, let's say, you could say smaller in terms of there's less of them, and to foreshadow what we're going to be doing, our row margins and our column margins will always be exactly the same. Those will be our sufficient statistics. Notice I'm not talking about minimally sufficient statistics, I'm just talking about sufficient statistics. You know, a lot of the stuff that we do here, you know, you can relate to stuff that's in Cassell and Berger, although especially a number of things that we do is not stuff that would be typically taught in 882 or 883, but I do like to relate you to that. So like page 399 of Cassell and Berger talks about calculating p-values conditional on a sufficient statistic, and that's very closely related to what we're going to do here. But even for any topic that we talk about, you should take a look at Cassell and Berger and see if there was something that's similar. Okay, so our p-value is going to look something like this. Note the little change there. It should be a little star. So that star means that we're taking with respect to our resample. So the probability star of t star, that's a random variable, being greater than or equal to the observed value of t in the original sample, given my sufficient statistic is the same as it was originally, and given the null hypothesis was true, that's going to be my p-value. If, let's say, only large values of t indicate evidence against the null hypothesis. And then we approximate this p-value through taking our resamples without replacement, just like what we did when we were just using the regular old bootstrap. You can also imagine situations where you have a two-tailed test or two-sided test, and you would need to make the corresponding changes to this, just like what we had previously. Okay.
So to calculate the p-value, would take it with replacement.
Just
Calculate the p-value. Do we take the resamples with replacement?
yes. No, I'm sorry. Without replacement. Do I have? Okay. Sorry. That was a result of copy and pasting stuff to relate to what we had before, and that was a big error. I apologize for that. You know, I even emphasized, you know, in capital letters there.
I was kind of confused because we were doing without replacement and suddenly the p-value.
Yeah. Sorry about that. So without replacement. And then that basically takes us to about 12:15. Are there any questions? Okay, that's it for today then.